recording now. So again, good morning, and we're going to get started here on a brief introduction to simulation. So just right off the bat, what is simulation? It's a design analysis tool that was based on FEM, which is the finite element method. It was first developed by a company named SRAC back in 1982. They came out with their first product in 1995 called CosmosWorks. They were one of the first gold partners to have a simulation type environment within SolidWorks. In 2001, they were acquired by Dassault Systems, and in 2003, SRAC was merged with SolidWorks Corporation, and that's what you're going to see today. So what is FEA? So FEA is a numerical technique for finding an approximate solution to a list of partial differential equations. Okay, and now these are used in a bunch of different industries: machine design, acoustics, magnetics, soil mechanics, fluid dynamics, structural, vibration, and thermal. Now we're going to talk about a few of those today. Mainly we're going to talk about structural, vibration, and some fatigue, just to get you guys just a brief rundown of exactly the kinds of things that you can do with simulation. So first off, whenever you're going to set up a problem for simulation, you want to set up your model. So we call this pre-processing. So number one is build the mathematical model. Now most of you guys are going to have that already created in SolidWorks, right? You're going to have some kind of model that you need to run an analysis on. But the idea is that you don't necessarily need all of the features that are in the model in order to get you a correct solution when it comes to FEA. So we're going to talk about that. We're going to talk about breaking down the mathematical model. So the next step would be to define the analysis. So whether it's a linear static analysis, thermal analysis, frequency, whatever it may be, that's the next step. Material definition, I've got this listed as the third step here, but this can also be defined within SolidWorks, so even before the analysis. And then identifying loads and restraints, and then a process we call meshing. And then after that, you run the analysis. There's not a whole lot that you can do after that. You just let it run. This can take some time. And then once the analysis is done, you would analyze those results through post-processing. And again, we're going to talk about all of this in a brief demonstration here at the end. So the first thing is, building the mathematical model. Whenever you start with a part, it may have too many features, maybe logos, fillets, chamfers, things like that. That's not really pertinent to the analysis. And here you can see I've highlighted those fillets in red. We may not need those when it comes to time to run the analysis. Another approach, a little bit more aggressive approach, would be to maybe go from a solid to a surface, and you can kind of see that here in this example. And we'll talk about this here in a second, what this means for an analysis. So next step in the process after you build that mathematical model would be to set up the mesh. So what is a mesh? Mesh is basically the process of splitting it into very fine elements, so finite elements through a process called discretization or meshing. And also, your loads and supports in the model are also applied to that mesh. They're actually applied to each individual node after the model has been meshed. So I've seen this happen a couple times where you might have made a change to that model, and when you go to run, the loads have to be applied to the mesh itself, so you might have to remesh before that stage, before going on to the next process. So again, here a little quick example. So we've got our ideal mathematical model, and from there we can break that down into finer finite elements with a mesh, and you can see that example there. So there's a number of different types of elements. The most basic type of element is a solid tetrahedral element. This example that I'm showing you here on the right is considered a draft quality element. These elements only have 4 nodes. Each node has 3 degrees of freedom, so translation in X, Y, and Z. We're going to talk about why there's only 3. Why are there not 6? Because we also need to account for rotation. But in a solid element, we're assuming that the model is rigid, that it's fixed on the ground. Okay. And then a more higher quality element has 10 total nodes. So not only in the corners, but also midpoint to each one of those elements. So we've got 4 corners and 6 midside, and again a total of 3 degrees of freedom per node. These are much higher quality elements. Each element can actually bend, whereas in this model, in the draft quality elements, the edges between nodes have to remain straight. So both these types of nodes these types of elements are ideal for cast or machine type shapes. Now there's other types of elements, and earlier on when we talked about a more aggressive approach to a mathematical model, you might want to use a shell element for that. So shells are only on the surface, and the thickness is more prescribed during the meshing. You can tell how thick or thin that model is. So these types of elements run much faster for complex type sheet metal parts. And you'll also notice here these have 6 degrees of freedom, so each node can actually translate and rotate in this type of model. And then the last type of element, which would be a beam element. These are automatically defined whenever you use weldments. It takes a look at the cross-section for each element, or for each solid body, and defines a beam type element. And for beam elements, the nodes are actually at the endpoints of each one of the beams, and again, each one of those endpoints would have 6 degrees of freedom. All right, so the next stage in the process would be to set up a static analysis. I don't know if anyone has seen this equation before, but this is the universal equation for motion, where the M would be the inertial matrix, the C would be our dampening matrix, and the K would be our displacement matrix. And so we would be solving for force over time. But in a static analysis, we're really taking out most of that from the equation, and we're only looking at the displacements. That's the first thing that we solve for. Also, something to keep in mind with static analysis is that loads are applied slowly. They're not forceful. They're not remember, time is not really a factor here. So loads are applied slowly and allowed to converge. Loads are also constant. It's also linear, and what I mean by linear is the force and the displacement are based on on a material curve that is linear. You know, when you start to exceed the yield in a material, the curve would look something, you know, like this lower red line here. But again, it's linear. We're solving for displacement first, and then once we've got our displacement, we can solve for stress and strain. It's also assuming only small deflections. All right. Now, some other things here. There can be some errors within the analysis, and you know, it's a buildup of everything. It's a buildup of, you know, starting from the beginning in the idealization stage, where, you know, when you create that model, you know, you may be taking out more detail than is needed. Other things like sharp corners, you're going to have stress risers in those corners, and you're going to have an unrealistic, you know, stress within that area. So these kinds of things can lead to, you know, some inaccuracies in your analysis. But as long as you are, you know, prepared for that and are understanding of that, you can get some very accurate analysis from this. So you know, as far as the model goes, it's always a compromise between solve time and accuracy. The more fillets or the more features and geometry that you have in the model, the longer it's going to take to run. But you're also going to have a more accurate model. And again, in the mesh itself, mesh can generate some inaccuracies because it is breaking it down into smaller, you know, more easily manageable elements. But you know, in order to get, you know, a more gradual curve around your model, you may have to increase that mesh size. But as a consequence, you're taking more time to solve. So again, it's a compromise between solve time and accuracy. Now, there are some things that can help you to cut down on these automatically. So there's I put this bullet point in here for an adaptive mesh. There is an option in there to automatically control that mesh size based on from solve to solve what the difference in accuracy is. And then solution errors. Of course, this is something that we can't control. You know, based on, you know, just rounding errors within the solver. All right, so we're going to go into just a brief demonstration here. We're going to talk about the steering bracket. It's part of the suspension system for a rally car. Essentially, we want to keep the stress below 150 megapascals. We want to design it for at least 1 million cycles of load. And we also want to do a frequency check to avoid frequencies in the range of 1 to 30 hertz. And the reason for that being, you know, we've got a wheel out here. It's going to be rotating. It's going to be creating some kind of vibration. So we want to make sure that it's that we're avoiding those frequencies, those natural harmonic frequencies within this bracket, so that we don't cause a failure. And again, here's just a little bit of setup on what we're going to do here. We don't need to analyze the entire model. All that we're concerned about is this one bracket because you know, this is a new part. The rest of the structure is already existing in the rally car, but we want to design a lighter, more efficient bracket for the steering setup here. So we're only going to analyze just the one assembly. And that's kind of the setup there and what we're going to do. So I'm going to jump over here into SolidWorks. And you can see I've got my entire assembly here, but I'm just going to go ahead and open up just this steering bracket here. All right, so the first thing we're going to do is, you know, we can take a look in SolidWorks here. You know, we can see that I've got some materials already assigned. So, that could have been done, earlier on in the process. We're going to go ahead and just start an analysis. So up here on my simulation tab, I've already got simulation running. That's under add-ins here. We can turn on SolidWorks simulation. Once that's turned on, you'll see a pull-down menu up here. So from here, we can start a study. You can see we've got a number of different analysis types in SolidWorks. We are going to be talking about static, frequency, and fatigue. Static is part of SolidWorks Premium, and some of these are part of Professional, and most of these are part of the Professional package, and then some of the like the dynamic, linear dynamic analysis is part of the Advanced Professional. But we'll go ahead and just start a new static analysis here. So in the tree here, so you can see we've got a tab down here at the bottom for our study, which is just the name, and I just left it the default name. You can see that we've already got our materials applied, but if we didn't have this applied, we could edit those. We can edit each one individually if we need to. I've just made them all an aluminum 6061. Next thing we can do is apply fixtures. So we're going to go with a fixed hinge here. So with the hinge, we want to hold these bolted sections down. So that hinge is going to allow those surfaces to rotate, but they won't be able to move axially or against the axis in the Y or the Z direction. But they will be allowed to rotate. And then we'll apply one more load here to the back face. We want to simulate that is attached to the back side of the rest of the assembly there, so we'll give that a sliding face. Next thing we want to do is apply our force. So we'll apply a force here. Just pick on that surface, and from here I want to adjust the direction. So I can use geometry from my model to do that. I could also use a datum plane if I wanted to. So we're going to apply that against our normal to the surface at 6,000 newtons. And again, following down the tree here, next we're at mesh, so I'll go ahead and create the mesh. And from here we do have some additional parameters if we wanted to adjust the mesh size. We do have a slider here, and you can see as I adjust that, those numbers increase or decrease. I'll just take the default values there. Alright, so there you can see it's been broken down into some finer elements. Again, very fast. So from here we can run the analysis. Very fast again, and from here we can take a look at our stress. That's the first thing that popped up. We can see our minimum and maximum values there. Now one thing I forgot to mention here is we have the ability to apply sensors in the model, and this is just part of SolidWorks here. Now I can apply things like for simulation here, I want to take a look at stress. Now we said that our maximum von Mises stress, we wanted that to not exceed 150 megapascals. So we can say if it's greater than 150, to notify me. We'll go ahead and add one more sensor here to, again, to simulation. We want to do this for displacement, and we want to see, if it exceeds let's say 0.1 millimeters there. And there, if you'll notice here, I've already run my analysis, but you can see that it's telling me what my maximum stress is here. It's also telling me that my displacement has exceeded what I had specified there. And we can see that when we go over here to our displacement. So if we're trying to optimize our model and we're trying to keep under certain values, these sensors would automatically rebuild, and they would show us in that what's wrong window whenever we exceed those values. Another useful plot here, we can define additional plots, one of those being factor safety. So we might want to take a look at all the parts here. What is the factor safety? Here we're looking at factor safety distribution, and you can see the minimum is 2.4. So 2.4 being we could apply 2.4 times our load and still be under the yield of the material. All right, so let's take a look at fatigue. So again, I'm going to create another new study here. We'll run a fatigue analysis. And what we want to do here is basically add an event. And this event is going to look at the previous study. So the previous stress study that we did, we're going to take those loads, and now we want to cycle them. So what it's telling us here is we have a couple of different options. This is going to be fully reversed, meaning it will go from 0 to 1 down to -1 and then back to 0. And we're going to apply this over 1,000,000 cycles. And we want to see what happens. There you can see materials are already defined, but what's important here for a fatigue analysis is this SN curve. So this basically tells us strength over time, over cycles. This is something that came out of the materials handbook. This is not something that I defined. So from here we can simply just run our analysis. And again, this is solving this based on the original stress analysis that we did. And what we're concerned about is the damage and the life. So here you can see for a total number of cycles, the life expectancy over the entire part. So you can see in these areas here, there are a little bit lower cycles. So it looks like approximately 5 million cycles is the expected life of this part. I'll also go ahead and show the damage here, and you can see that based on the cycles that we gave it, with 1,000,000 cycles, we're at about 18% damage. All right, now the last thing that we wanted to look at is the frequency. So again, we're going to run a frequency analysis here, so starting a new study for this. And again, I could be renaming these each time, but you can see next to the tabs down here at the bottom, it does show the study type, little picture of that. But I could have easily given these a name, for frequency, fatigue, and for stress. Now the other thing that we want to do here, we want to use all of our same fixtures and loads from our previous stress analysis here. So instead of having to redefine those, I can just drag and drop those right here into study 3. Okay, and we can go back here to our stress. We're going to grab these loads as well. And so there you can see we've got, back here in our frequency study, our fixtures and loads are already applied. So again, we'll go ahead and just run this analysis. And what this is telling us here is because we've got some loads here in our analysis, we need to change our study type. That's really easy to do. Just come over here and tell it that we're going to use a different solver. So again, I can run my analysis. All right. And what we're looking at here are the natural frequencies. So this first one that popped up here, we can see that this first mode shape here, this first natural frequency is about almost 3,500 hertz. So we're well outside the boundary for our analysis. If you remember here back at the beginning, we wanted our frequency range to be between 1 or to avoid frequency range 1 to 30 hertz, and you can see we're way outside of that boundary. So how, what does this look like? So basically that part is able to move up and down. So that's the first natural frequency. If we look at mode shape 2, this one is going back and forth. And again, it tells us up here at the top what that frequency is. So you can see that first shape was the lowest frequency, so we're way outside the boundary here. Now we can also look at a full list of the resonant frequencies, and there you can see again that those frequencies are well above the values that we were looking for. Now it only evaluated 5 different mode shapes here, but that's an option in the solver. We can check for as many as we want. All right, guys. So we're right on a half an hour there. So hopefully you guys got some information out of this. And switch back to the slideshow here. So hopefully no one has any questions. If you want to put it into the side chat there, if you have any questions, I can answer those for you right now.